Now, what potential do bioresins have? Our next speaker, who has more than 20 years of industry experience in injection molding, says about them, bioresins, unmasking the superhero of sustainable materials in injection molding. In 2005, Oliver joined Husky Technologies, a leading injection molding company, as a test lab and service technician, progressing through the roles of application engineer and senior application engineer. Since 2019, he has been the leader of the hot runner application engineering team, EMEA. Oliver is a state-certified engineer and state-certified technical business administrator. Today, he continues to drive innovation and excellence in his leadership role at Husky, leveraging his industry experience, academic qualifications, and leadership skills. And now I would like to welcome Oliver Schindler from Husky Technologies with his presentation on the topic Bioresins in Injection Molding Applications, Benefits, Challenges, and Opportunities. Welcome, Oliver Schindler.
Thank you very much and welcome to the audience here and in front of the screens and behind of the screens. Thank you for the introduction, and I'm proud to be here to present Husky Injection Molding Systems as a global leader for injection molding equipment, injection molding machines, hot runners, molds, systems, and controllers. Yeah, to give you some. I need to go a slide back, an agenda. So first is we speak a little bit about the growing opportunity about bioresins. We will have a short overview about commercial available bioresins. We will speak about bioresins and the challenges and best practices, what we have learned. We will speak about bioresin application examples and how we can enable you to succeed. The growing opportunity of bioresins, I think we had quite interesting sessions this morning already, which shows that there's a huge interest from different kind of interests. It's the consumer itself. The consumers are more and more interested in buying some bioresins or some packages which are made from biomaterials, sustainable materials. And then we have companies who are adopting with their ESG initiatives, so environmental, social, and governance initiatives, to a kind of to adapt on bioresins and the usage of bioresins on their products or on the packages to show their contribution to the sustainable and to the planet. And then last, the legislation. We're getting more and more of the regulations from, example, EMEA. They are restricting petrol-based materials on single-use plastics. And this will come probably in more and more countries. So the interest will grow, and therefore we will be impacted as injection molding supplier as well. Then a short overview about commercial bioresins. What are bioresins? Biopolymers, biomaterials, however you want to call it. It's a material which is made from whole or from partial sustainable, or not sustainable, from renewable resources like corn, maize, tapioca starch, potato starch, vegetable starches, sugar grain starch, or wood pulp cellulose, for example. What are the commercial bioresins and what they replace? So we have been a lot of contact with customers in the packaging market, and in the packaging market we experience that they want to replace very often PP, PLA, PPP, HDPE, LDPE, and PET as well, and polystyrene. And they are replaced by PLA, PHA, PHB, and cellulose-based materials. Some key terms on what bioresins means. So bio-based, like I said, is partially or whole made from renewable resources. And is not mandatorily mean that it's biodegradable. Biodegradable means that it would break down in a natural environment, which, like I said, bio-based doesn't mandatorily mean. And there's a key term of compostable, where we need also to differentiate between the industrial compostable and the home compostable products. And yeah, we are challenged, like molders, mold makers, and as well injection molding companies, with kind of material characteristics which are a little bit unknown, which are unknown and different to a polypropylene or to a HDPE. And we speak here about viscosity. The materials always behave very viscous in comparison to PPs. They are like PET, or very often like PET. They are having a high tendency on leakage and weepage. They have a temperature sensitivity, which is much worse than, let's say, a polyolefin, which can easily withstand 30 minutes into a barrel without burning. And very often they be having corrosive. Manufacturability. So, like I said, often customers are coming to us and they want to replace just a polypropylene product to a bio material. And this is the first challenge, that probably the product itself is not able to be molded in a bioresin with the existing wall thicknesses. Packages are often about 3.3 millimeters of a wall thickness, and therefore take already higher pressures with polypropylene, and then to use a biomaterial is giving a challenge. And as well, the material characteristics as well is a challenge. Here I want to speak more about the temperature sensitivity, like you see hopefully here, like that. The material can easily burn, and then you can contaminate your system easily, and in worst case you need to hot clean the system, manually clean the system as soon as you do burn the material. Performance, so customers need to consider that maybe existing machine capacity is not anymore sufficient enough. The balancing of the system is maybe different because you have less capacity, you have a higher temperature sensitivity or impact on the balancing, and as well the longevity of your components are impacted by using bioresins. And the last point is quality. Maybe customers cannot maintain any more existing standards, existing quality tolerances, and for that they maybe have to consider higher performance variation, and as well they need to think about the longevity of products. Here are 3 examples. On the left side you see that is a hot runner manifold plug. So it's inside the manifold sitting there, and the melt will go along the angled surface you see there. And you see that there's a highly corroded area, which is even not in the direct melt stream. Then on the middle picture you see a nozzle tip. It's also within the hot runner. Also here it's corroded at a position which is not directly in contact with the material, so it's purely about gases. And then you see on the third picture on the right, this is a cavity, a core of a coffee cup tool. And you can see as well there's corrosion affected. So even molders, mold makers are having to adapt their technologies, their steels they are using to this kind of materials. Some other examples from the weepage and leakage point is that on the first picture on the left you see it's carbonized black material. As soon as it is degraded, the material intends to flow everywhere in the gaps. Everywhere means that in worst case you have really to dismantle the system, disassemble, cleaning it, and then to bring it back into production. And on the 2 other pictures you see that's a valve gate piston, which usually is intended for being open and closing the valve stem. But underneath you can see there's some material buildup, what we call weepage or leakage, which is going between the valve stem to the back in underneath the piston and then blocks the actuation. So what are the best practices on how we can act on optimizing this? First of all is optimizing the application design, then optimizing the hot runners and controller, optimizing the manifold design of the hot runner, and to ensure a consistent preparation of the material. Let's go to the next slides a bit deeper on these points. First of all, when you are in contact with us at Husky, we have global application engineering team with experts. They have the capability to pull a lot of toolboxes, simulation assistant software. So the first point when we are in contact with replacing a conventional product with a bioresin, we would ask the customer for cavity fill analysis. And also here we have kind of challenges. Not all the materials are yet characterized to be able to run into a mold flow simulation. So here we would need to go into contact with the resin supplier and to deeply discuss with them on what we can do on simulating on a best possible way. Maybe we find some substitute or they have some characterization available already, but not officially implemented yet. On top of that, we have resin test labs in different kind of countries, and we are offering each time when there's an unknown material for us to make a material test so that we can learn the extremes, how the material behave in our systems, how we can support you on finding the best solution for your product and for this material. And review of thermal FEA is one of the points Husky is doing for each hot runner system. We are performing a thermal FEA prior we start any manufacturing of the system to ensure that we have a close, and especially for bioresins, a narrow temperature over or undershoot. Evaluate for high pressure guidelines. This is more or less important to understand if we need to build our system stronger or if we can apply our standard rules. And often underestimated is the low delta temperature at the gate. We would need to maintain a low temperature at the gate because especially biomaterials have a low melting point and can impact negatively the injection point quality if we are not sure that the gate is cold enough. So what do we do? So we need first of all to check, do we apply the corrosion resistant standards? It's not for all biomaterials necessary. We will apply V-pitch mitigation components, means we will apply tight tolerances, probably applying some coatings. We recommend to use plunger valve gates to have always a clear gate cutting and a nice gate quality over a long time. Individual tip control is always recommended. There's sometimes the idea to group control. We would always intend to have an individual tip control. Improve heat distribution all along the system and ensure that you have an I/O connection from the controller to your machine, that for any cycle time interruption, it is shutting down automatically to a safe temperature, that this kind of burning, like you see here, cannot happen. Optimize the manifold system is that Husky geometrically and rheologically balance all the hot runner systems based on low pressures, reduce shear rates, minimum residence time. So that is what we do for each system prior we ship and manufacture. And what we also recommend is to avoid bridging manifolds often, and this is common, that you have an heater from the manifold on the injection side and clamp side, and they are bridged together. We recommend to not do that. We recommend to keep them individual with two thermocouples so that you can have an individual thermal interaction in case you need. And important, like I said before, uniform and balanced thermal profile all along from the inlet to the outlet to the cavity, that we ensure that there's no specific overshoot or undershoot in the system which can damage the material. And the last and important point is when you buy a manifold system, so without hot runner plates, the cooling is in hand of a mold maker. The mold maker should respect our rules on cooling. So here a short overview on what kind of inputs we need to run a mold flow based simulation. We call it melt channel sizing optimization. So we would ask the customers for the resin, that's clear. What are the additives? Are there any specific information we should know from the resin supplier? What are the processing parameters? What are the drop locations? What is the part geometry and the performance requirements? For example, do you have specific cycle time targets? Do you have targets on color change? Do you have balancing targets? And if so, we can all put this into our mold flow based software, and this software will optimize the system based on best pressure drop, shear rate in the system, shear rate at the gate, and for sure residence time. Then the last point 4 is especially for molders. So always as a molder, ensure that you are using or that you use dry materials before you do it. Avoid any exposing to atmospheric conditions after drying, so maybe an on-machine hopper, or try to avoid any longer exposure to the atmospheric conditions. Keep the package sealed until it's ready to use. Reseal any unused material, and always important, follow the supplier recommendations on the drying time and temperatures, as well as melt and mold temperatures, screw speed, back pressure speed, and as well the total residence time. So that means the hot runner plus the machine is the total residence time. Some few examples, recent ones. I have some as well with me today. So for the audience here, we can have a later look a bit deeper on that. Here I summarized what we are doing. So cutlery is quite common. Replacing polystyrene between 4.6 and 6 grams. And here we are going to high cavities, 32, 48 drop, even 64 drop. So we have here already some experience. Coffee capsules are known as well. PLA, replacing polypropylene in that case. We are going here in these examples from 2.9 to 5 grams, and a wall thickness of 0.6 with partial going down to 0.15 on the breakage areas. And here we speak as well from 4 to a high cavity system, 48, even 69. 62, sorry. PLA, a cap. This one is a prototyping tool, 2.2 grams, 0.8 millimeter of a thickness, and it's a 4-drop, so there's nothing particular to say. We have a kind of large range of interest from customers on different products. Not all products I can show here, so that's why I go to the next slide and tell you more about on how Husky can enable you to succeed. So we have the experience, the expertise, and the technology. Like I said, we have a global team. The global team has access to mold flow, FEA, CFD, and as well the resin test lab. The resin test lab, I have here as well with me a few examples. We have a kind of a Petri dish, which is flexible between a 0.5 of a millimeter wall thickness up to 3.5. It's a 2-drop system, and we can run it in different kind of hot runner versions, from the smallest nozzle to almost the biggest series we have, and as well as hot tip or valve-gated solution. Then we have kind of addressing the packaging market, a cup, drinking cup, which is known. Here we have 0.4 to 0.7 millimeters of a wall thickness, as well a bigger core or bigger thicknesses of 0.6 to 0.9 millimeters. It's a single cavity system. And as well here we tested different kind of bioresins. Coffee capsule, this is kind of, it's called the Tassimo design. The Tassimo design is a 4-drop ultrasync E hot runner. As well here we can provide you with a different kind of wall thicknesses between 0.3 to 1.6 individually. Adjust them and doing trials as close as possible to your application. Globally, we have much more tools, and this is still only an excerpt here, but I'm focusing more on the packaging and on the thin wall coffee pot market right now. And you see that we have from 4 to 48 drop large scale of possibilities at Husky to support and simulate the product you are interested in. So this is what we can serve you with, is with expertise, technology, and experience. And the key to success, we built up or engineered the Ultramelt technology. The Ultramelt technology is a product from Husky which is especially to address the challenges of a bioresin delivery. Means melt pass is all made from stainless steel. You will have everywhere tight gaps. We will have potentially some coatings on areas which are critical, and there is a risk of the minimizing of corrosion is given here.
Thank you very much. Oliver Schindler from Husky Technologies. Yeah, it was an interesting, very exciting lecture, and yeah, you have the possibility to ask questions now. Okay.
One question. Are you satisfied with the input you get from material suppliers or customers regarding material information?
So that's a very good question. Yes, I'm very satisfied. There's a lot of cooperation with different kind of resin suppliers. We are doing in Luxembourg a lot, and I know that we do as well in the US right now a lot of working together with resin suppliers. And I think there's a lot of small suppliers on the market, which we understand that it's quite impossible that each material they develop, they can characterize for simulation. But we have every time a very close relationship with them. We work together with them. We invite them to come to either Luxembourg or to US laboratory to make kind of testings and to experience themselves on what are the challenges with hot runners and hot runner products or machines, and to learn with us together. Yeah. And I think the second question was about customers. Yes, the customers are very cooperative as well, but often it's more on the supplier side, because for our customers, the materials are also new. That means they need also to learn a little bit more about that, and for this we need the help of the suppliers.
Yes, I just asked
because
of the newness of those products, and you have a lot of small developers, and it's not sure that they always can supply a technical data sheet, for example.
Yeah, and this we have very often the case that we just get, you should keep a certain range of temperatures for the melt, and that basically everything is unknown. Yeah, we are very familiar with this.
Are there any further questions from the audience? I mean, here are a lot of people developing resins, what we've heard today.
Sure.
Excellent.
Thanks for the great overview. How would you rate it, moving from PE or PP to PLA? Is it more difficult? Is it more easy?
It's difficult.
How would you rate that?
It's, like I said, it's really a challenge, and it's very often that, for example, this kind of thin wall packaging market is what we are contacted very often in. It's not that you can just replace the polypropylene by a bioresin, by PLA in that case, because the pressures from PLA is going more in direction of a PET. That means from the hot runner point of view, we need to adapt our hot runners on bigger channel sizing to release the pressure, but also your cavity design maybe needs to be adapted from the wall thickness point of view.
Okay, so the tool has to be modified accordingly?
Probably yes. Yeah, it can be challenging that you just change from one to the other. But like I said, we have the capabilities. We have a kind of tools available which we can make some trials with you to understand the material better. And also for PLA is one of the material which behaves quite corrosive. So you should also think that the equipment you are using right now is maybe not capable to withstand the corrosiveness.
Okay, thank you.
Welcome.
Martin, do you have a question?
I don't have a question, but I'd like to encourage everybody of you to contact the Husky guys. From my past in compostables, I have very good experience working with you. You have a lot of tools. You have for sure the best equipment available in Luxembourg as well as in Canada. So yeah, feel free. Don't be too shy. It's worth to trial and to teach also others about compostables, because as you said in the beginning, Oliver, the whole market needs to transform. They need to learn. Our compostables are quite new, different shrinkage, maybe different corrosion, depends on the compound, by the way, and also depends also on the performance. Maybe you need to adapt your compound to the existing tools which are there and to perform the same way as polypropylene. Not in terms of shrinkage, but maybe in terms of cycle time. Yeah, thank you, everybody. And thank you, Oliver, in particular. And
thank you. Thank you very much for the presentation, Oliver Schindler. Thank you.